So the two most common hardware description languages that you see in the world today, one is called VHDL, Very High Level Description Language or something, and the other is Verilog. And this is a very sophisticated, in terms of a language, this is a very sophisticated way of describing the behavior of a circuit. And in fact, the actual sort of low-level behavior, the idea that if I AND together two, 1 bits, I get out a 1 bit. If I AND together a 1 and a 0 bit, I get out a 0 bit. Behaviors of how things like logic work, those are, that's not built into this language. This language is really a general purpose thing of values flowing around. They get combined by operators. And in this language, you can describe the behavior of the operators and the different types of values you may have. So you can sort of simulate almost any system this way. The top level of the design is this hierarchy of entities, and the entities can have multiple architectures. So I could have an entity called an adder, but it might have different architectures. I might have a ripple carry adder, and a carry select adder, and a carry look ahead adder. So this is sort of an abstraction mechanism that lets us talk about the behavior addition of two 32-bit numbers. And then I can have a bunch of architectures that each implement that with different sort of size and performance trade-offs. And then I have a configuration that tells me which architecture to choose for which of the entities. This is very elegant. In fact, if you do circuit design for the government, they require you to use VHDL. The rest of the world, just in the same way that C is a very popular language, it's not terribly powerful, but it gets the job done and allows you to pretty efficiently specify what you want in terms of behavior, even though you give up a little bit in terms of sort of elegance and abstraction. That sort of corresponds to what Verilog will do for us. It has it knows about Boolean logic. It has a 4-valued logic, just like JSIM. Not completely surprising. I was involved in the first of the Verilog simulators, and I seem to have gotten stuck into four-value logic world. And so he asked me to write a simulator. It's going to have 4-valued logic. And the design is composed as a hierarchy of modules. So modules and dot subcircuit are virtually identical. It does, in JSIM, we do strictly a structural approach, right? Each subcircuit is just a listing of other subcircuits or gates and how to wire them up. So we're just showing you the structure of how to put things together. We're not doing anything at all in terms of behavior. In other words, JSIM is completely all about describing the actual implementation, which is all we really want to do in this course. But you'll see in the next couple of slides how we talk about behavior in a way that solves a lot of the little nudgy, JSIM is really sort of writing assembly language. You can understand what's going on, but it's sort of, in the end, sort of slightly tedious and painful. So the question is, what would you choose to do instead? And Verilog was the answer that was created to help a lot of engineers do digital system design at something above the logic gate level. So here's an example of a Verilog description. In this case, it's of the register file. And here we have a module, and down here we have the end of the module. So this looks sort of like a procedure call, right? So what we're going to do is to describe the module in terms of the inputs and outputs the module has. In this case, you can see some of the inputs are logically just single bits, a clock or the right enable. Other inputs are little buses. In this case, the RA1 signal is the 5 bits for the A address going into the register file. Down here, what we see is now a description of the behavior of the register file. We're not really trying to describe exactly how the register file should be built in terms of single or multi-port memories, the deep low-level logic. We're just trying to describe the behavior. So this is an array declaration. So this basically says, this is a 32-element array and this number here is telling me how many bits there are at each location of that array. So in this case, the indices of the bits go from 31 down to 0. So this is a 32-bit words, and there's 32 of them in the array. And here I have a very simple description. I said, look, what comes out on the read data port, in this case read data 1? Well, if the RA1 is equal to 31, I want a 0, otherwise I want the contents of the file. And you know what the logic gates are that implement that. You had to figure those out for yourself. Here I've just sort of described the behavior that I wanted. You know, for a particular value of the address, I want to get a 0, otherwise I want to access the register file. So this is a fairly compact representation that it gets more and more powerful. You'll see, I'll show you the PC in a second. You'll see it's actually, you know, just a short couple lines. It's much shorter than the write-up. It's much shorter than the JSIM, but it is a complete specification of what the behavior is. Now what about registers? How do registers work? Well, you'll notice that we have a register type, sort of declaring some signals that will be the outputs of registers. And then down here, what I'm doing is I'm pointing out that this particular piece of behavior description only applies at the rising edge of the clock, at the positive edge of the clock. So when there's a positive edge of the clock, if WRF is 1, then take the write data and write it into the register file at the write address. Right, all the details about you know, how to actually implement a register, back-to-back flip latches and all that, that's all hidden away here. And whether this is actually going to use some sort of memory primitive or maybe even a big array of single-bit, you know, deregs, that's really up to the compiler to figure out, depending on what you've asked it in terms of performance and area. So this is a very, you know, short and sweet. What are some goals you might want to have in a behavioral description? Well, you might want to be able to read it and understand what's happening. So my claim is that even without a lot of training, you can sort of make good guesses about what the behavior is that's being described. Somebody had to come change this behavior. Who knows what, you know, the 70-second AND gate in your design accomplishes in the JSIM description? Here, it's pretty easy to identify where a behavior is being described and modify that behavior if you want. So at this level, if I wanted to also have R0 read as a 1, it's pretty clear how to do that. It's less clear about how to modify your JSIM. You know, you'd have to know a lot more about the details of the implementation, whereas it's a lot easier to work at the behavioral level. Here's the program counter. The thing I really want to point out here is, a plus sign. Right? So, you know, not only are there sort of logical operations, you know, testing whether something is true or not and selecting one thing or another, which is sort of the behavioral description of a MUX, and doing simple logic expressions, but this idea of actually letting the system worry about how to actually implement the arithmetic operators, add, subtract, multiply, that's something that, again, Verilog does very efficiently for you. So this is a description of the PC. We actually had to go, you know, we had several pages describing all the different things that have to happen in terms of exceptions and resets, and, you know, what happens to bit 31. So this is a description that actually captures all that. It's very short and sweet. These braces here are basically making a bundle of wires. So for example, this is basically saying, take the 31-bit PC Inc value, which I've described up above here, and so you can see over here it's a 31-bit value, and concatenate that with bit 31 of the old program counter, or IA31 in our parlance, to make a 32-bit PC value. So this is actually a fairly elegant notation, and again, my claim is that you would find it easy to change the behavior of the program counter logic here, much more easy than you would if you went back to your circuit. So what do we do with these descriptions?